Before humans built telescopes, the night sky was nothing more than a sea of mysterious points of light. As technology advanced, we began to see galaxies, glowing nebulae, and colossal stellar explosions. But the deeper astronomers looked into the universe, the more they kept encountering regions of absolute darkness, places where the familiar laws of physics seemed to stop working. Those regions are black holes, one of the strangest and most baffling objects science has ever discovered. A black hole isn't literally a hole punched through space, nor is it a giant cosmic vacuum roaming the universe and swallowing everything in its path. It forms when matter is compressed to an unimaginable extreme, creating gravity so intense that not even light, the fastest thing in the universe, traveling at nearly 186,000 miles per second, can escape. Because no light can leave, a black hole is almost completely invisible. The only way we know it's there is by observing its effects on nearby stars, clouds of gas, and even the fabric of space-time itself. Surrounding every black hole is an invisible boundary known as the event horizon. It's not a physical wall, but rather the point of no return. Once anything crosses this boundary, every possible path leads inward toward the center of the black hole. No signal, no beam of light, and no piece of information can ever come back to tell us what lies beyond. That fundamental limit has turned black holes into nature's most extreme laboratory, a place where Einstein's general theory of relativity collides with quantum mechanics, exposing questions that modern physics still cannot fully answer. What's even more fascinating is that there isn't just one kind of black hole. Some are only a few times more massive than our sun, born from the deaths of giant stars. Others contain tens of billions of solar masses, sitting at the centers of galaxies and influencing the evolution of systems filled with trillions of stars. Beyond those are entirely hypothetical black holes that exist only in mathematical equations, where physicists push the limits of nature itself in search of a unified theory of the universe. In this journey, we'll explore every known type of black hole, from those that have been directly observed to the boldest predictions of modern theoretical physics. Each one reveals a different piece of the puzzle surrounding gravity, space-time, and the origins of the cosmos, while reminding us why black holes remain one of the greatest mysteries science is still striving to unravel.
1. Stellar black holes, the final legacy of massive stars. Of all the black holes we've discovered, stellar black holes are by far the most common, and they were the first type ever confirmed to exist. They don't appear out of nowhere. Instead, they're the final stage in the life of a star, at least about 20 times as massive as our sun. For millions of years, these massive stars maintain a delicate balance between two opposing forces. Outward pressure generated by nuclear fusion constantly pushes against gravity, while gravity relentlessly tries to pull the entire star inward. This cosmic tug-of-war continues until the star finally runs out of nuclear fuel. At that moment, the star's core completely loses its ability to resist gravity. In an incredibly short period of time, the core collapses at an astonishing speed, crushing matter into densities almost beyond comprehension. Meanwhile, the outer layers are blasted into space in a brilliant supernova explosion, an event that can briefly release more energy than an entire galaxy. If the remaining core is massive enough, no known force in nature can stop the collapse from continuing. Matter is squeezed into an unimaginably tiny region where the escape velocity exceeds the speed of light, marking the birth of a black hole. What's truly astonishing is that a stellar black hole typically contains anywhere from about 3 to well over 100 times the mass of our sun, yet its diameter is only a few dozen miles across. Imagine compressing the combined mass of dozens of suns into a space no larger than a city. That incredible density bends space-time to such an extreme
that anything wandering too close becomes trapped by its immense gravitational pull. Since black holes themselves emit no light, astronomers have to detect them indirectly. One of the most common methods is by observing an accretion disk. When a black hole pulls gas from a nearby companion star, the material doesn't fall straight into the center. Instead, it spirals inward, forming a rapidly rotating disk. Friction between layers of superheated gas raises the temperature to millions of degrees, causing the disk to emit powerful X-rays that can be detected by space telescopes. Another method is to track the motion of nearby stars. If a star appears to orbit an apparently empty region of space while being tugged by an enormous invisible mass, it's strong evidence that a black hole is present. The biggest breakthrough came in 2015, when the LIGO and Virgo observatories made the first direct detection of gravitational waves produced by the merger of two stellar black holes. For the first time, humanity had a completely new way of observing the universe, not through light, but through ripples in space-time itself. One of the most famous stellar black holes is Cygnus X1, located about 7,000 light-years from Earth. It was the first black hole to gain broad acceptance within the scientific community and has a mass roughly 21 times that of the Sun. Its special place in history is tied to a memorable scientific story. Physicist Stephen Hawking once made a friendly bet that Cygnus X1 would turn out not to be a black hole. As the observational evidence became overwhelming and the conclusion impossible to deny, Hawking cheerfully admitted he had lost the bet. For him, it was a perfect example of what science is all about: being willing to change your mind when the evidence demands it. Today, astronomical models suggest that the Milky Way may contain millions of stellar black holes. Most of them remain completely invisible because they aren't actively pulling in surrounding matter and therefore emit no electromagnetic radiation. They drift silently among the stars like invisible gravitational traps, revealing themselves only through their influence on nearby objects, or when they collide and merge with another black hole, sending ripples racing across the very fabric of space-time.
2. Ultramassive black holes, the giants that rule the universe. If stellar black holes are born from the death of massive stars, ultramassive black holes represent an entirely different level of nature's extremes. They are the most colossal version of supermassive black holes, with masses exceeding 10 billion suns. Some observations even suggest they may reach 40 to more than 70 billion times the mass of the Sun. As far as we know today, these are the heaviest objects ever discovered in the universe, possessing enough gravity to control the motion of trillions of stars within giant galaxies. Unlike stellar black holes, the origin of these gravitational monsters remains one of astronomy's greatest unsolved mysteries. Current theories suggest they began as smaller black holes that steadily grew by consuming gas, dust, stars, and by merging with other black holes over billions of years. However, astronomers have also discovered incredibly massive black holes that already existed when the universe was still in its infancy, just a few 100 million years after the Big Bang. That means they must have grown far faster than our current theoretical models can explain. One of the most famous examples is TON 618, the black hole at the center of an extraordinarily bright quasar located more than 10 billion light-years from Earth. It is estimated to contain roughly 66 billion solar masses, making it one of the largest black holes ever discovered. The quasar's incredible brightness doesn't come from the black hole itself. Instead, it comes from the superheated disk of gas spiraling around it. As this material is compressed and accelerated to speeds approaching the speed of light, it releases so much energy that the quasar can outshine an entire galaxy containing hundreds of billions of stars. Another remarkable example is Homburg 15A, located at the center of the Abell 85 galaxy cluster. Its central black hole is estimated to weigh around 40 billion times the mass of the Sun,
making it one of the most powerful gravitational cores ever observed. The existence of black holes like Holmberg 15A reveals just how closely giant galaxies and their central black holes evolve together, continuously shaping one another throughout the history of the universe. To appreciate the sheer scale of a black hole like TON 618, imagine replacing our Sun with it overnight. Its event horizon would stretch far beyond the orbit of Neptune, engulfing nearly the entire solar system. Even light itself, which travels at nearly 300,000 kilometers per second, would need more than a week to cross from one side of the event horizon to the other. That staggering scale reminds us just how enormous the warped region of space-time surrounding these cosmic giants truly is, far beyond anything our everyday intuition can grasp. The existence of ultra-massive black holes doesn't just expand the upper limits of what objects in the universe can become. It directly challenges our understanding of how black holes form and evolve. They suggest that the early universe may have contained extraordinary conditions that allowed certain black holes to grow at an almost explosive rate. Every new observation of these giants offers another clue about the universe's earliest chapters, while raising profound questions that science has yet to answer.
3. Intermediate mass black holes, the missing link in the universe's evolution. For decades, astronomers have faced a fascinating paradox. They have confirmed the existence of stellar black holes, weighing anywhere from a few to several dozen times the mass of the Sun. They have also observed supermassive black holes, containing millions or even billions of solar masses at the centers of galaxies. Yet between these two extremes lies a puzzling gap with very little convincing evidence. This raises an important question. How did the universe produce gigantic black holes if there was never an intermediate stage? To answer that mystery, scientists propose the existence of intermediate mass black holes, one of the most important missing pieces in our understanding of black hole evolution. According to current models, intermediate mass black holes range from a few hundred to around 100,000 solar masses. They're far larger than black holes formed by collapsing stars, but still thousands of times smaller than the supermassive black holes found in galactic centers. If they truly exist in large numbers, they could represent the building blocks that gradually merged in accumulated matter over billions of years to create the enormous black holes we see today. Finding these objects, however, has proven far more difficult than scientists originally expected. Most intermediate mass black holes aren't actively feeding on surrounding matter, meaning they don't produce the brilliant accretion disks or dazzling quasars that can be detected across billions of light years. Instead, they blend almost perfectly into the darkness of space, leaving behind only subtle gravitational fingerprints that astronomers must painstakingly search for. One of the most effective methods is to study globular clusters. By tracking the motions of thousands of stars orbiting their dense centers, researchers can infer the presence of an invisible object with enormous mass. 47 Tucanae, one of the Milky Way's most famous globular clusters, has repeatedly been identified as a possible candidate for hosting an intermediate mass black hole. Meanwhile, dwarf galaxies have become another key target, since their relatively quiet environments may preserve ancient black holes that never grew into the colossal monsters found in larger galaxies. Among the strongest candidates is HLX-1, an X-ray source located about 290 million light-years from Earth. Observations suggest it contains roughly 20,000 times the mass of the Sun, placing it squarely within the predicted range for an intermediate mass black hole. Whenever HLX-1 pulls material from its companion star, the gas is heated to extraordinary temperatures, producing intense X-ray outbursts that allow space telescopes to detect its presence. Although the list of candidates continues to grow, intermediate mass black holes remain one of modern astronomy's greatest mysteries. If their existence is confirmed beyond doubt, they would become the long-sought missing link connecting stellar black holes to supermassive black holes, helping explain how relatively small objects in the early universe eventually evolved into the colossal gravitational engines that dominate galaxies today.
4. Kerr Black Holes,
when space-time itself is swept into a cosmic whirlpool. When most people think of a black hole, they imagine a perfectly still region of darkness where gravity simply pulls everything inward. But reality is far stranger than that. Most black holes in the universe don't just possess enormous mass, they're also spinning at incredible speeds. These are known as Kerr Black Holes, named after New Zealand mathematician and physicist Roy Kerr, who discovered the solution describing them within Einstein's general theory of relativity in 1963. The existence of spinning black holes is almost inevitable. Before they die, stars are already rotating on their own axes. When a massive star's core collapses under gravity, its angular momentum must be conserved. It's much like a figure skater who spins faster by pulling in their arms. As the collapsing core shrinks, its rotation speeds up dramatically. The result is a black hole that inherits not only the mass of its parent star, but also its rapid spin. What makes a Kerr black hole extraordinary isn't just the black hole itself, it's the way it reshapes the fabric of space-time around it. According to general relativity, mass bends space-time. But when that mass is spinning at tremendous speeds, it creates an even stranger phenomenon known as frame dragging. Instead of space-time merely sagging like a stretched sheet under a heavy ball, it begins twisting like water spiraling down an enormous whirlpool. If you were to approach a Kerr black hole, gravity wouldn't be the only force acting on you. Space-time itself would already be moving. That means everything, from clouds of gas and dust to planets and even light itself, is dragged along by the black hole's rotation. The closer you get to the center, the stronger this effect becomes, creating one of the most extreme environments ever predicted by modern physics. Surrounding the event horizon of a Kerr black hole is a remarkable region called the ergosphere. Shaped like a stretched sphere, it sits just outside the point of no return. Inside the ergosphere, the normal rules of motion begin to break down. No object can remain stationary relative to the rest of the universe. No matter how powerful your engines are or how hard you try to resist, you are forced to move in the same direction as the black hole's spin. Space-time itself behaves like a raging river, carrying everything within its current. The existence of the ergosphere led to one of the boldest ideas in astrophysics. In 1969, physicist Roger Penrose proposed a mechanism showing that a spinning black hole's rotational energy could actually be extracted. According to the Penrose process, an object entering the ergosphere could split into two pieces. One fragment falls into the black hole, while the other escapes carrying more energy than the original object possessed. That extra energy comes directly from the black hole's rotation. The Penrose process isn't just an elegant mathematical concept. It may also explain how spinning black holes power some of the most violent phenomena in the universe, including the colossal jets that shoot millions of light years from the centers of active galaxies. These streams of matter can carry more energy than the combined output of billions of stars. Today, observations suggest that many black holes are spinning at speeds remarkably close to the maximum allowed by the laws of physics. That means these immense gravitational engines don't merely warp space, they set the very fabric of the universe into motion. In the realm of Kerr black holes, gravity is no longer the only force shaping reality. Space-time itself becomes a swirling current, sweeping everything into its enormous cosmic dance.
5. Charged black holes, Reisner-Nordstrom and Kerr-Newman black holes. Mathematical solutions that push general relativity to its limits. In the familiar picture, black holes are typically described by two fundamental properties, mass and rotation. But the equations of general relativity allow for another possibility. If a black hole carries either a positive or negative electric charge, its entire structure changes. A non-rotating charged black hole is known as a Reisner-Nordstrom black hole, while one that both spins and carries charge is called a Kerr-Newman black hole. These are exact mathematical solutions to Einstein's field equations combined with electromagnetism. significantly expanding our understanding of extreme gravitational objects. In theory, a black hole could certainly form from electrically charged matter. As the collapsing star shrinks, its electric charge would be preserved alongside its mass and angular momentum. That charge generates an electric field that acts alongside gravity, altering the shape of the event horizon, the surrounding space-time, and the paths that matter and light can follow. For this reason, charged black holes serve as ideal theoretical models for exploring behaviors that ordinary black holes cannot clearly exhibit. In reality, however, the chances of finding one in the universe are extremely small. Interstellar space isn't completely empty. It is filled with plasma, along with countless electrons and protons moving at high speeds. If a black hole carried a positive charge, it would rapidly attract negatively charged electrons from its surroundings. If it carried a negative charge, it would instead pull in positively charged protons. This process continues until the black hole's charge is almost completely neutralized. Because of this, most physicists believe that nearly all naturally occurring black holes are electrically neutral, making the discovery of a truly charged black hole extraordinarily unlikely. Although they are probably rare in the observable universe, charged black holes play an essential role in theoretical physics. They appear frequently in studies of general relativity, where scientists test exact solutions to Einstein's equations under the most extreme conditions imaginable. In string theory, charged black holes also serve as important models for connecting gravity with quantum mechanics. They have further contributed to our understanding of black hole thermodynamics, including entropy, Hawking temperature, and the deep relationship between information, energy, and the structure of space-time itself. The greatest value of Reisner-Nordstrom and Kerr-Newman black holes isn't that they're common in nature. Their true importance lies in the way they push Einstein's equations to their absolute limits. Through these mathematical models, scientists can test the stability of gravity under the harshest possible conditions, while searching for the first clues of where general relativity and quantum mechanics may ultimately merge into a single unified theory of the universe.
6. Quantum black holes, where the two greatest pillars of physics collide. Among all the types of black holes ever proposed, quantum black holes are perhaps the most mysterious and the hardest to imagine. They aren't enormous gravitational monsters lurking at the centers of galaxies. Instead, they're predicted to be smaller than an atom. At such an incredibly tiny scale, the two most successful theories in modern physics, general relativity, which describes gravity, and quantum mechanics, which governs the subatomic world, can no longer operate independently. They are forced to coexist within the same physical system, creating one of the greatest unsolved problems in science. According to theoretical models, quantum black holes can only be fully described at the Planck scale, where distances shrink to around 10 to the negative 35th meters. This is so unimaginably small that it's far beyond the reach of any instrument we have today and is widely considered the smallest meaningful length in physics. Below this scale, the familiar concepts of distance and space-time may no longer exist in the way we understand them. Instead, the fabric of the universe itself could become discrete, constantly fluctuating, and dominated by quantum effects. Unlike massive black holes, quantum black holes have extraordinarily short lifetimes. According to Hawking radiation, quantum effects near the event horizon gradually cause a black hole to lose energy and mass over time. For a black hole this tiny, however, that process would happen incredibly fast. It would evaporate almost instantly after forming, releasing an enormous burst of energy before disappearing completely. That fleeting existence is precisely what makes detecting one so incredibly difficult. Physicists have proposed several possible origins for quantum black holes. One possibility is that they formed during the earliest moments of the universe, when temperatures and energy densities were vastly higher than they are today. Another hypothesis suggests they could be created in extremely high-energy particle collisions at the Large Hadron Collider, LHC, but only if extra spatial dimensions exist, as predicted by certain theoretical models. So far, however, no experimental evidence has confirmed the existence of quantum black holes, and they remain purely hypothetical. Even so, their scientific importance extends far beyond the objects themselves. If quantum black holes were ever discovered, or even described accurately through mathematics, it would represent one of the greatest breakthroughs in the history of physics. They could provide the missing path toward a theory of quantum gravity, unifying gravity with quantum mechanics, and bringing humanity closer to one of the ultimate goals of modern physics, a true theory of everything, a single framework capable of explaining every fundamental force and every physical phenomenon in the universe.